Hello. In the previous lecture, we discussed the public key encryption scheme RSA. In this lecture, we will discuss another public key scheme, namely Diffie-Hellman. So, Diffie-Hellman algorithm is a public key crypto system. It was invented before RSA. Unlike RSA, it cannot be used for encryption or to create digital signatures. However, the utility of Diffie-Hellman is that it allows two individuals, say Alice and Bob, to agree on a shared secret key, even though all the messages exchanged by Alice and Bob over a network can be overheard by intruders. So, Alice and Bob are connected by a network, and any message sent by Alice or Bob can be overheard by an intruder. Despite this, Diffie-Hellman algorithm allows Alice and Bob to agree on a shared secret key. So, the only communication that Alice and Bob can do is over the channel, and this channel can be intercepted by intruders. We will now discuss Diffie-Hellman, which allows Alice and Bob to agree on a shared secret key in this context. Once Alice and Bob have agreed upon a shared key, it can be used for communication using symmetric key cryptography. So, suppose the shared key that Alice and Bob have agreed upon is KS, then this can be used as the symmetric key in a symmetric key cipher such as DES or AES. So, Diffie-Hellman algorithm operates as follows. There are numbers P and G where P is a large prime number. For example, we might require 2048 bits to represent P. G is a number less than P. P and G can be publicly known, they do not have to be kept secret. An example is Alice might choose P and G and then send them over the channel to Bob. So, if this means is used to share P and G, then P and G may be overheard by intruders. After agreeing upon P and G, each of Alice and Bob then independently chooses a large number less than P at random and keeps it secret. So, Alice chooses a secret number less than P and Bob independently chooses another secret number less than P. Let SA denote the secret number chosen by Alice and let SB denote the secret number chosen by Bob. So, we have that SA is less than P and SB is less than P. SA and SB have to be large because otherwise if they were small, then the intruder could just try out numbers starting from 1, 1, 2, 3, 4 and so on. So, just by trying a few numbers, the intruder might be able to guess SA or SB. So, hence SA and SB are large, but they must be less than P. So, the scheme works as follows. Alice computes TA equals G to the power SA mod P and Bob computes TB equals G to the power SB mod P. Then Alice sends TA to Bob and Bob sends TB to Alice. Now, Alice has received TB from Bob. Alice computes TB to the power SA mod P and then similarly Bob computes TA to the power SB mod P using TA which has been received from Alice and SB which is Bob's secret value. Now, the claim is that TB to the power SA mod P equals TA to the power SB mod P. If we prove this, then it will follow that the value computed by Alice and the value computed by Bob are the same. So, Alice and Bob have agreed upon the secret key which is equal to TB to the power SA mod P and it is the same as TA to the power SB mod P. This theorem is quite straightforward to prove. The LHS can be written as follows. Just by substituting TB equals G to the power SB mod P, we get that the LHS is G to the power SB mod P the whole to the power SA mod P. Now, using the properties of modulo P arithmetic, we get that this is the same as G to the power SB to the power SA mod P, which is in turn the same as G to the power SB mod P. Now, notice that this is symmetric in A and B. So, similarly, the RHS is also equal to the same quantity G to the power SA SB mod P. So, hence LHS equals RHS, which proves this theorem. Thus, Alice and Bob have agreed upon the same number G to the power SASB mod P, which is a shared key. Subsequently, Alice and Bob can use this shared key as the symmetric key in a symmetric key cipher such as DES or AES. So, this is Diffie-Hellman's algorithm. SA is known as Alice's private key and TA is known as Alice's public key. Similarly, SB and TB are known as Bob's private and public key respectively. So, as the name suggests, SA and SB are secret, hence they are known as private keys, and TA and TB are sent over the channel where they can be sniffed by intruders. TA and TB are hence public. Here's an example. Let P be 23 and G be 5. So, P is a prime number. Let SA be 4 and SB be 3. So, in this example, the values of P, SA and SB are very small. In practice, they are obviously much larger. Now, TA is G to the power SA mod P by definition. So, it is 5 to the power 4 mod 23, that turns out to be 4. Similarly, TB is G to the power SB mod P, and it turns out to be 5. So, if we calculate 5 to the power 3 mod 23, then it is 10. Now, TA to the power SB mod P, which is the value computed by Bob. So, it is 4 to the power 3 mod 23, and that comes out to be 18. Similarly, TB to the power SA mod P is 10 to the power 4 mod 23, and it comes out to be 18. So, in this example, Alice and Bob have agreed upon the shared key 18. So, notice that Alice and Bob have both obtained the same number 18, which is the shared symmetric key. Now, let us discuss the security of Diffie-Hellman. Recall that G and P are publicly known in general, and TA and TB are sent over the channel, and hence they can be sniffed by intruders. So, even though an intruder may know G, P and TA equals G to the power SA mod P and TB equals G to the power SB mod P, it is computationally infeasible for the intruder to calculate G to the power SA SB mod P. So, let us understand why this is true. If G, P and G to the power SA mod P are known, then the problem of finding SA using these quantities is known as discrete logarithm problem. The reason for this nomenclature is the following. Consider the equation G to the power SA equals TA. So, if TA is known and G is known, then we can find SA by just taking logarithms on both sides. Log base G, if we take log base G on both sides, then we get SA from G and TA. So, this is the ordinary logarithm problem. Now, we have in this problem we have G to the power SA mod P. So, because of the presence of this mod P, this is the discrete logarithm problem. So, the discrete logarithm problem is computationally hard to solve. So, if the intruder could compute discrete logarithms efficiently, then he or she could find the secret keys SASB, and hence once SA and SB are found, then it is straightforward to find G to the power SASB mod P. But no efficient algorithm is known for finding discrete logarithms. So, the security of Diffie-Hellman rests on this fact that there is no efficient algorithm known for finding discrete logarithms. So, recall that the security of RSA was based on the fact that there is no efficient algorithm known for factoring a number n into its prime factors p and q. In contrast, the security of Diffie-Hellman is based on the fact that there is no efficient algorithm known for finding discrete logarithms. Now, there are some additional requirements on P and G for the protocol to be secure. The security of Diffie-Hellman is compromised unless P and G satisfy the following additional properties. One property is that G to the power x mod P must not equal 1 unless x is a multiple of P minus 1. Now, first notice that if x is a multiple of P minus 1, then we get that G to the power x mod P equals G to the power, let us call it y times P minus 1, since x is a multiple of P minus 1, this mod P. So, this can be written as G to the power P minus 1 mod P the whole to the power y mod P. So, by the corollary to Fermat's little theorem and Bezout's identity, which we discussed in the previous class, So this equals g to the power p minus 1 mod p equals 1. So hence this is equal to 1. So g to the power x mod p equals 1 clearly whenever x is a multiple of p minus 1. But we must have the property that g to the power x mod p must not equal 1 unless x is a multiple of p minus 1. So the reason is this, if g to the power x mod p equals 1 for a small value of x, that is for example a value of x much smaller than p minus 1, if g to the power x mod p equals 1 for a value of x much smaller than p minus 1, then to find SA using g to the power SA mod p by brute force, an intruder would just need to try out a small number of values of SA. So the intruder might start from SA equals 1, then SA equals 2, SA equals 3 and so on. So if g to the power x mod p equals 1 for a small value, then the intruder would quickly find an SA which satisfies g to the power SA mod p equals TA. For example, suppose g to the power 3 mod p is 1. So x equals 3 satisfies this property that g to the power x mod p is 1. Then g to the power 4 mod p is g mod p, g to the power 5 mod p is g squared mod p, g to the power 6 mod p is 1, g to the power 7 mod p is g mod p and so on. So these values keep on repeating in a cycle and the period of the cycle is very small. So in this case the intruder just has to try out a few values of SA to get a value of SA which satisfies the equation g to the power SA mod p equals TA. Since this expression g to the power SA mod p has only a few distinct values, so it's straightforward to find an SA which satisfies g to the power SA mod p equals TA, which is the target. Another property that must be satisfied is that p minus 1 by 2 must also be a prime. So apart from p, p minus 1 by 2 must also be a prime. A prime that satisfies this property is called a safe prime. For example, consider p equals 7. 7 minus 1 by 2 is 3, which is also prime. So 7 is a safe prime. Consider p equals 11. 11 minus 1 by 2 is 5, which is also a prime. So 11 is also a safe prime. Now consider p equals 13. 13 minus 1 by 2 is 12 by 2, that's 6, which is not a prime. So 13 is not a safe prime. So we must always choose p such that it is a safe prime. The reason is that if this property is not satisfied, then it may be possible to efficiently compute discrete algorithms using an algorithm known as Pauling-Hellman algorithm. We omit the details, but for our purposes, we only need to know that we choose p such that p is a safe prime. Now there is an attack on Diffie-Hellman called man-in-the-middle attack. Bob. The man-in-the-middle attack is when there is an intruder, say 2D, who intercepts the communication channel between Alice and Bob and can modify messages before sending them to the recipient. So when Alice sends a message to Bob, 2D can intercept that message, modify it and then send it to Bob. Similarly, when Bob sends a message to Alice, 2D can modify the message and then send it to Alice. Such an attacker is known as a man-in-the-middle attacker. Diffie-Hellman algorithm is insecure when there can be an intruder called man-in-the-middle on the channel between Alice and Bob who can modify messages sent from Alice to Bob or vice versa. Suppose again that G and P are publicly known. When Alice receives TB, there is no way for her to find out whether it was really sent by Bob or not. And even if it was sent by Bob, was it modified during transit from Bob to Alice? So 2D might just initiate communication and set a value to Alice, and Alice has no way to find out that it was sent by 2D and not by Bob. Also, if Bob sends a value to Alice, 2D might modify it before sending it to Alice. So hence this is true that when Alice receives TB, there is no way for her to find out whether it was really sent by Bob and whether it was modified during transit. So there is similar uncertainty when Bob receives TA. So Bob doesn't know whether it was indeed sent by Alice and whether it was modified during transit. Now this illustrates a man-in-the-middle attack where Mallory is the intruder, who is the man-in-the-middle attacker. In this figure, Alice sends the public key A equals G to the power A mod P towards Bob. Now, Mallory, who is the man in the middle attacker, intercepts this message, and instead of relaying it to Bob, what Mallory does is she chooses her own private key small z and computes the corresponding public key z equals g to the power z mod p, and then sends capital Z to Bob instead of sending A. Similarly, when Bob sends his public key capital B equals g to the power b mod p to towards Alice, Mallory intercepts that message. Mallory does not send capital B to Alice. Instead, Mallory sends capital Z equals g to the power z mod p to Alice. Now, after performing the computations of Diffie-Hellman, so Alice computes k equals z to the power a mod p, and Bob computes kb equals z to the power b mod p, and Mallory computes k equals a to the power z mod p and kb equals b to the power z mod p. Notice that this k is the same as this k and this kb is the same as this kb by the proof that we earlier discussed. So, what has essentially happened is that Alice and Mallory have agreed on this key k, and Mallory and Bob have agreed on the key kb. So, at the end of the attack, Alice has the secret shared key g to the power az mod p with Mallory, that is the same as k, and Bob has the secret shared key g to the power bz mod p with Mallory. But Alice and Bob think that they have a secret shared key with each other. So, this is what this attack has done. So, it leads Alice and Bob to think that they have a secret shared key in common, whereas each one of them has a secret shared key with Mallory. So, after the intruder has performed this man in the middle attack, when Alice sends an encrypted message to Bob, the intruder Mallory can read it and modify it before forwarding it to Bob. So, the intruder decrypts the encrypted message by using the shared key between Mallory and Alice, and then modifies the message, and then re-encrypts it using the shared key between Mallory and Bob. Similarly, the intruder can read and modify messages from that are sent from Bob to Alice. Hence, the form of the Diffie-Hellman algorithm that we discussed above is only secure against so-called passive attacks, in which the intruder just watches messages being transmitted between Alice and Bob, but doesn't modify any messages being transmitted. So, if the attacker is active, wherein the attacker can modify messages sent between Alice and Bob, then this Diffie-Hellman algorithm is not secure. So, let us discuss ways to modify the Diffie-Hellman algorithm so that it can defend against the man in the middle attack. So, as a first attempt, suppose after completing the Diffie-Hellman algorithm, Alice encrypts and transmits the established shared key to Bob to prove that she is indeed Alice. So, the shared key is g to the power SA SB mod p. Suppose after completing the Diffie-Hellman algorithm, Alice encrypts and transmits the established shared key, which is this one, to Bob to prove that she is indeed Alice. So, will Bob be able to detect a man in the middle attack? No, because the intruder can encrypt and send a shared key established between the intruder and Bob to Bob. Bob thinks that he has a shared key with Alice, but actually Bob has a shared key with Mallory, who is the intruder. So, the intruder can just break this scheme by encrypting and sending the shared key established between the intruder and Bob to Bob. So, this scheme does not defend against the man in the middle attack. Another possible scheme for defending against the man in the middle attack is the following. Suppose P and G are public. Recall that SB is Bob's private key and TB is Bob's public key. In this scheme, the public key of every user is stored in a database like a telephone directory. When Alice wants to establish a secret key with Bob, Bob does not have to send this public key to Alice. Instead, Alice just looks up the public key TB of Bob from the database like the telephone directory and computes TB to the power SA mod p. Similarly, Bob looks up Alice's public key TA from this database and then computes TA to the power SB mod p. Recall that TB to the power SA mod p equals TA to the power SB mod p. So, Alice and Bob have agreed upon this shared secret key. So, does this defense work? So, it does work under the assumption that Alice can securely connect with the database and obtain Bob's public key, and similarly Bob can securely connect to the database and obtain Alice's public key. So under these conditions, this scheme works. This scheme works because Alice is able to securely get Bob's public key, and Bob is able to securely get Alice's public key, and once this has been done upon a shared secret key, which is this. The crucial question is, how do we implement a database in which the public keys are stored? So later on we'll study how this database in which the public keys are stored can be implemented. This is called public key infrastructure. This database needs to be such that users Alice and Bob can connect to the database and securely obtain the public keys of other users. So later on we'll discuss how such a database can be implemented. Such a database is a part of what is known as public key infrastructure. So we'll discuss public key infrastructure later on. This concludes our discussion of Diffie-Hellman algorithm. With this, we have concluded our discussion of cryptography. In the next lecture, we'll discuss message integrity. Thank you.